and share the screen. Okay. This was the problem we talked about. I'm going to switch to slide quickly, but the problem is like this. The ball falls freely from this height of 4 feet. It's the ground that has an angle. Hitting the ground and bouncing back, this part is impact with ground. And as you may see, is an oblique impact because it comes with one angle, it may go with another angle. And right after it leaves point A, it simply becomes a projectile motion. It's going to have a velocity and an angle, goes all the way and hits the ground again. The problem gives the time of travel from A to B. You want to find the distance, and we want to find the coefficient of restitution. So let's go to the solution. So this is what we did on Monday. As I mentioned, the problem has 3 steps or 3 stages. One is when it goes from 1 to A, is a free fall. It was conservation of energy, we solved it. The second one is right at the impact, which is 2 before impact and 3 after the impact. And it's oblique impact. And we started working with this and we didn't finish. So let's continue that. We found the velocity here. We found the velocity just before impact. At 2 and 3, or between 2 and 3, it is oblique impact. Right? So ball is one object, as I said, ground is the second object. For the ground, the velocity before and after will be 0. So you don't have to find the velocity of ground after the impact is already known. It allows you to lose one equation. That equation, as I mentioned, will be this: conservation of linear momentum for the entire system, because while the velocity of ground is 0, at the same time, the mass of ground, which is technically Earth, is infinity, so you can't solve this. So we're going to get rid of this equation. The good point is, because the ground has 0 velocity, what I need to find is the vertical and tangential component of velocity after the impact. So I only have 2 unknowns for V3, and I need 2 equations. One is going to come from conservation of linear momentum in tangential acceleration for particle B, and the other one is the coefficient of restitution. Any question up to here? Or you guys even don't remember any of this from Monday, right? Hopefully you remember some. So that was the status. If that's the case, let's find those components. Considering the slope we have here is 3, 4, 5. If I call this angle as my theta, then Which one of these two will be theta? This guy or this guy? 1, 2. Is 1 equal to theta or 2 is equal to theta? This is something you need to know so you can move forward. All right. We're going to have a midterm next week. So let's say this is a midterm problem. Please say something, some volunteer. Which one is theta, 1 or 2?
I think y is theta.
Sorry?
I think y is theta.
Y is theta, yes, because if you consider here, this is 2, and then 1 is going to be theta. So if that's the case, and this is theta, then the tangential component of velocity, which is this guy, I'm going to use equation 2. I can cancel out this m and this m because it's the same. So v2t, which is going to be v2 sine theta, and sine theta is 3/5, right? And this will be v3 tangential after the impact. So v3 tangential, if you calculate this, the velocity was 1605. You multiply by 0.6. 16.05 times 0.6 gives you 9.63 feet per second. So this is one of the unknowns. Okay. Equation 3. Any question about this? We just project the velocity into tangential direction and say this guy is the same. So we got that. Now, if we go to equation 3, as I said, the velocity of ground is 0. So this is going to be 0. This is going to be 0, right? So what you get is this. If I write equation 3, you're going to get minus V2n times E equals V3n, right? We do not know n, but V2n, look at here for a second, please. V2n is this component, right? And that component is V2 cosine theta. So it's going to be V2 cosine theta, which is going to be 16.05 times 0.8. Which gives you 1284 feet per second. I'm going to substitute here. So we're going to get minus 12.84 times E is V3n. So you calculate your V3n, of course, in terms of E. Make sense? I used conservation of linear momentum in tangential direction to find T component of V3, and I used the coefficient of restitution equation to find the N component. Now, if I redraw this part again down here, remember you have this is ground, right? The ball comes like this. And bounces back like that. This is V3. How I can find this angle? Let's call it theta 3. If this is V3N, and now you see why you have this negative sign, because when it goes down, approaching, this is V2N, this is V3 in opposite direction. So obviously, remember these are vector equations, so it's negative, which means it goes up. And this is V3T. So I can simply find this angle theta 3, right? Theta 3 is going to be tan inverse of V3 tangential divided by V3 normal. Okay. Now, you may realize that if I put the numbers, theta 3 is going to be tan inverse of a number over E. So you're going to get tangential component, which is 9.63. In the denominator, you have 12.84. Remember, this is just a value, so I don't put the number, E. So this is not really helpful, is it? Because we cannot continue with E in the tangent, and you have to have sine and cosine and all of that. So it makes complicated, right? So then how you solve this? Let's go back to the projectile motion for now. Remember this velocity? Oops. This velocity has one x component and one y component, right? It's going to be like V3x and V3y. Right? You guys follow? Now, and on the path, you have the distance d. So this is going to be dx or sx or whatever you name it. This is dy. So dx if it has a velocity and it has x component and y component, right? So in x direction, you're going to have d0 plus vx times t. And d0, if you put your reference here, it's going to be 0. So technically your dx is going to be v3x times t. How much is dx here? If this angle is again theta 3, 4, 5, and let me see if I pick the right d. Yeah. Okay. So you're going to get dx is going to be 0.6 d is equal to v3x times t. Right? Sorry, it's going to be 0.8 because this is 4. Okay. You guys follow? Any question? So this is the velocity after the impact, right? I found its normal and tangential direction, but normal and tangential are in these two directions. I have my own x and y direction, right? So for now, I project this into x and y direction. This is going to be v3x. It's going to be v3y. And if I write the equations in x direction, this is what I have. In y direction, I get dy is v3 y t minus g by 2 t squared, right? These are equations for projectile motion. And if I substitute that, dy is going to be 0.6d, and that is equal to v3y t minus g by 2 t squared. Remember, t is given. T is 0.5 second. So I'm going to substitute the value of t here in both equations. This is equation 1, and this is equation 2, like Greek letter 1 and 2. So from 1, you simply get 0.8d equals 0.5 v3x, because time t is equal to 5. In the second one, you're going to get 0.6d equals 0.5 v3. This should be y. Y minus 32.2 by 2 times 0.5 squared. And if you calculate this, 32.2 divided by 2 times 0.5 squared. It's going to be 4.025. This is the new equation 2, and this is new equation 1. Any question? Do you guys follow? So I just separated the projectile motion, analyzed it, got these two equations. Let me write them side by side. 0.8 d equals 0.5 v3x and 0.6 d plus sorry, I'm going to take this to the right hand side just to make it simple. Plus 4.025 equals 0.5 v3y. Okay. I have two equations. How many unknowns I have here? I have three unknowns. One is d, one is vx, one is vy. Right? Do you guys follow? Okay. Now, let's go back to V3, to the geometry of V3. See how I can get X and Y component in terms of T and N. Okay? I'm going to redraw that vector or the vector components here. Let's say, again, this is your, what happened? This is your surface, right? Which is 3, 4, 5. And this is the perpendicular direction. Okay. You have the final velocity components. I'm going to use this blue big arrows. This is one component. That's too big. You know what? Let's just go with. I'm going to make the lines green so I can get the vector. So the y component of vector this is your V3N, right? And you had a tangential component. I'm going to do it with red. This is your V3T, correct? If this is my overall velocity, yellow I think is not visible. Let me just go with another color. If I get the overall velocity, which was V3, like that, And I want to get the X and Y component of this, obviously, right? Can I get the X and Y component of this guy and this guy and add them together to get these two components? Can I do that? Yes or no? Kelly, if I get the X and Y component of this yellow highlighted vector and add them together, do I get these two or not?
I'm not entirely sure, but it would make sense that it would work.
It would work. Why? Because remember, what are X and Y or N and T components? They are vectors in certain directions, right? Technically, and I want to draw your attention to the very basic concept. When we say V3X is something, V3Y is something, which that means V3 is V3X as a vector plus V3Y as a vector, right? That's what we do. We divide it into components. These are technically, these are the vector component of this velocity in X and Y, right? Now, if I say V3 is also V3N plus V3T, these are also vectors, right? Now, if I write V3N as V3NX plus V3NY, can I do that? Because this yellow vector, I can get its X and Y components, right? Do you guys follow? And then I can also say, okay, V3T as a vector is V3T X component plus V3T Y component. Can I do that? So practically, I get my N and T component of velocity into X and Y. If I add them together, you're going to get V3 is going to be V3NX plus V3NY plus V3TX plus V3TY, right? Now I'm going to get the X components together and Y components together. So you're going to get V3NX I plus V3 E XI plus V3 N YJ plus V3 EYJ. Technically, this is what I have, right? Then if I get them together, you're going to get V3NX plus V3TX I plus V3NY plus V3 tangential, the Y component, J. Of course, this makes it V3X, and this makes it V3 3y, right? Can I do that? So technically, I could not get v3x and v3y directly. So I used, and now let me clean this mess a little bit. So I got, it doesn't, oops. I got this component and this component. I'm going to get their x and y components and then add them together to get x and y component of V3. Does it make sense? I see some confused. Aaron, do you follow? I can't hear you.
Kind of. So why couldn't you just use like the tangential, just substitute for the x slot and not do the x portion of normal and the x portion of tangential?
That's what I'm doing. You see, when you say tangential, because why I can't do that? Because the projectile, look at here, look at the projectile motion is about x and y. Okay. So when I write the equation, these are my final equations from projectile motion. Right? Which gives you V3x and V3y, right? It doesn't give you in terms of normal tangential. I try to find the angle so I can get x and y, but the angle has tangent of E in it. If we knew E, right? If the problem had given us E, it was easy. If we could get this angle, right? Get the horizontal, vertical, it was very easy. But because E is not given, you cannot go like tangent of E and you want to get sine and cosine. It's very complicated, right? It's highly nonlinear. You cannot solve it. That's why I go back to these two components, get their x and y components and add them together. I'm going to give you like a financial example. Imagine you are running a company and you have 5 projects, right? Each of them, they had a budget and a profit, positive or negative profit, right? What is the total profit of your system? You add the profits of all projects together, right? And you add the budgets of all systems together, the overall number becomes your overall budget. The overall number for profit or loss, negative, positive, will be your overall loss, right? Does that make sense? So let's say this is this vector. Let me clean this a little bit again. Let's say this vector that I highlight here with purple is your financial system. This is your profit and this is your budget, right? Kind of like that. And now this is one project and this is another project. If you want to find the overall budget, you say, okay, how much money I spend here, how much money I spend here, I add them together, my budget. How much money I make here, how much money I make here, I add them together because it becomes my profit, right? Does that make sense? We do the same with these components. I want to find the x and y component of V3 And V3 is made of this and that. I find X and Y component of this, X and Y component of this, and add them together. Okay? Make sense now? I don't hear anything. Jake, looks good. Jake B. We have like the other Jake. Looks okay. So if that's the case, I'm gonna clean this a little bit again because that's kind of messed up. Let me just move. Oops. You know what? Let's just take the axis, move it down, and do it again. Because so we have this component of velocity like V3n. Oops. And we have V3t. And this is 3, 4, 5. I technically need to find, and let me do one with black, one with red, so we know what we are doing. Okay. I need to find this component and this component. Considering this is theta, this is also theta. So V3 tx is going to be V3t times cosine theta. And V3t y is going to be V3 tangential sine theta. Right? And it is negative. Remember, this velocity is negative. So let's just put the negative signs here so we make sure we go with the sign. Because when we talk about Vx and Vy, or we can just keep it later, we add the negative positives one way or another. For the n component, if this is theta, then this is going to be theta. So V3n, the x component, hold on. The x component is cosine. This is theta. The x component is cosine again. How is possible? So maybe V3n it should be sine theta if this is theta. And this is theta. And this is okay, this is theta. If this is theta, this will be theta. My bad. So this is going to be V3n sine theta, and V3n y is going to be V3n cosine theta. Okay. I'm going to bring back the two equations these two equations here. Okay. And move them all the way back. Okay. So these were my two equations from projectile motion. And these components have to be added. So let's put it this way. The yellow components of velocity comes here. Those green components of velocity come here. So I'm going to substitute those and write it down as, okay, 0.8d is equal to 0.5 V3t cosine theta. Let's just put the number. Cosine theta is 0.8. And plus V3n 0.6, this guy. And for the second equation, 0.6d is equal to half V3t sine theta, which is 0.6, plus V3n 0.8. And you had another parameter here. Let me just write it down here. Okay. Looks good. Now, if I substitute, remember, V3n is this much and V3t is this much. I'm going to substitute these values. Now, for this part, remember, this is negative, this is positive. So we're going to have to put negative here. Now, if you look at these two equations, the two unknowns are D, oops. D and E, and you can solve it for D and E. I'm going to give you a minute to substitute the numbers and solve the values. Any question? Did you guys get the number by the way? These are the numbers you should get. Let me know if you get the same numbers.
I have a question. Why is minus 0.6?
Because this guy, right? You're talking about here?
Yeah, exactly.
Okay. If you look at the components of velocity for tangential, the x component, oh my God, this is just not working. The x component is positive, the y component is negative. For n, both of them are positive. So when I add them, I put just the values here. When I add them, this goes down, so I have to subtract it.
Okay.
Because
Yeah, I
these
was
are
just-
still vector components, right?
Yeah.
I could write
Yeah.
it here. It might have been easier.
Yes.
I could write it here, for example, here, I go with negative. I put a negative sign here and then keep going. But I just put the values when I add together, I consider the negative positive signs.
Thank
Did
you.
you guys get the same numbers? So I think this problem had a little bit of everything. It's a lengthy solution. I mean, I have to explain some of the things that you should know for now. We had, please stop writing for a second. I'm going to explain the whole process again. So we had a simple case of conservation of energy, right? Then we had impact, and then we had projectile. We solved the energy easily. I mean, just one equation. We solved the impact and got our equation, right? This guy and this guy. Then we started with the projectile, trying to find out the displacement, velocity, position relations, right? And then because I didn't have these components, the rest was just explaining you how you can get Vx and Vy from these two components. Now, hopefully you learned it. The next time you just simply get xy's. You shouldn't take this much time. Okay. Any question or comment about this? Okay. Let's just go back to the slides. I think we have done enough of this chapter. So we did this example. We did this example and this example. So I'm going to review what are the things we learned. This was just oblique impact, right? Straightforward, getting the X and Y's and equations. This was a direct impact, but parametrically, if you solve this problem, this is kind of similar to what we did. It goes from A to B. Look at here for a second, please. It goes from A to B with a certain velocity. If you know the length and everything, you can determine how much it goes. And then when it hits here, it bounces with a different direction, lower maybe velocity, different direction, and then goes less. So again, you have a projectile, impact, projectile. So you can try that. This was again similar to the first problem we solved. You have an impact here between the two, then B is going to hit the wall, another impact with the wall. We explain how the wall works. This was the most complicated. So we kind of covered different types of impact problems involving a little bit of kinematics and other stuff. Any question about this chapter? Are we good? Okay, I'm going to give you 5 minutes break and then we're going to start chapter 16. Let's stop sharing and I'm going to share the screen. And we're going to start rigid bodies. So a quick review of what we have done so far in the past 3.5 weeks. We talked about kinematics of rigid bodies, velocity, acceleration, motion, displacement, and stuff like that. We develop equations, we use different coordinate systems to solve problems. Then we start kinetics using Newton's second law. After Newton's second law, we used work energy method. And after that, just in the past chapter, we used impulse and momentum. We technically are going to go through the exact same steps for rigid bodies. This chapter is about kinematics of rigid bodies, velocities, accelerations, displacement, and things like that. And the next chapter is going to be implementation of Newton's second law for the kinetics. After that, work energy. After that, impulse and momentum. And now you may say, why the heck we repeat everything again? You will see with the definition of rigid bodies, we are creating a new physical quantity, which makes the motion and all of the equations different. And that is when you have the size and dimension for a rigid body. Up to now, everything we analyze, we assume it is a mathematically like a single particle with no dimensions. Even if it was an airplane or a car or a boat or a human, swinging in a park or a soccer ball someone kicks, they all have dimensions. But we assume they move like a point from one point to another, right? Now we're going to see what happens if we are going to have dimensions. Okay. So first of all, what we do here is a two-dimensional motion. That means the motion happens in plane. Most of the things we analyzed in chapter 12, 13, 14, 15, they were two-dimensional. Some of the problems were like three-dimensional. You could just add z to it, like x, y, and z, or nt and z, or things like that. For rigid bodies, if you make it three-dimensional, it becomes way more complicated. And I'm not going to go into that. That's kind of more advanced. I think there's a chapter for three-dimensional dynamics in every dynamics book, but I don't cover that. Most mechanisms we deal with use rigid bodies in a two-dimensional motion, as we'll see. So first, we talk about translation of rigid bodies. Just they move and they do not rotate, because I'm going to explain briefly because you know it from your physics courses, right? One difference between particle and rigid body is that rigid body has a size, and when it has a size, is not just translate as a point. I don't know if you can see my hand here, this guy. So, or maybe just something smaller. If you have a piece of paper like this, it can move and it can rotate, right? And it can rotate and move together at the same time. So the rotation part of the rigid body that comes to play makes a lot of changes in the equations we have. So to be able to analyze rigid bodies, we start, like always, from the simplest case. We suppose the rigid body does not rotate, just translates, no rotation, everything moves parallel to its original position. Then if just translates, it could be rectilinear or curvilinear like a part. Practically, translation of rigid bodies is like, maybe they're like a particle. Everything moves together. Rectilinear and curvilinear motion. Then we talk about rotation of rigid bodies. They rotate about a fixed point. Like, give me an example of something rotates about fixed point. No one uses mechanical watches anymore, right? Everybody has this digital stuff. But if you have a mechanical watch, the arrows just go rotate about fixed point, right? When you sit in your car and don't move, and you turn the steering wheel rotates about fixed point. So there's a lot of motion, type of motion. I think that one example could be one of these, what's called the wind turbines, right? That they create clean energy. And some people believe also they create cancer or something, right? So those rotate about fixed point. So these are examples of rotation about fixed point. Then we have general motion, which combines rotation and translation, like what? When, I don't know, like when you throw a ruler to your friend from one side to another, it moves and kind of rotates and turns around. And we analyze this type of motion for two-dimensional case, which means everything moves in a plane. Any question about the general concept? So we start with rigid bodies. And let me give you some example of rigid bodies. I don't know how visible it might be. This guy, the way this guy dances, the arms go around. These are like rotation of rigid body. That's kind of like a funny guy. Another example. So of course, these are fun examples, but I want you guys to pay attention to this. This humanoid made by matchsticks, you see, each of those parts are rigid body. Some of them are fixed, so make rotation about fixed point. Some of them make general motion, but when you look at the whole motion, it creates rigid body motion. So to start with this rigid body motion, I think first we need to define what is rigid body. And I always, here it says a system of particles that the distances between the particles remain unchanged. That's kind of vague definition, but kind of scientific definition. Let me ask you this, as mechanical, or some of you might be civil engineers, do we have anything that is rigid? Rigid means does not deform, right? The distance between particles remains the same. Do we have, give me an example of something that is rigid?
Atoms. Like
Very interesting.
compounds.
Very interesting example. I would say, first of all, atoms do not have dimensions, right? Practically, they're very small. And remember, I'm glad you brought this up. Remember, anything we deal in this course and most of the courses you do is for macro scale, right? We are in a Newtonian space with Newtonian rules. When you go to the molecule level or atom level, you go to quantum mechanics and atomic forces. So every rule is different, right? So I wouldn't say an atom is rigid because it's practically like very, very small single point, right? And if you consider electrons around atoms, because atoms are made of electrons, protons, and neutrons, right? Considering electrons move around the atoms in different, spaces, maybe we shouldn't say atoms are rigid. But I like your example because it brings the discussion. I'm glad you brought this up because I want to emphasize that F equals MA does not apply in atomic level, right? Or molecular level. There's a different type of mechanics involved. We don't go there. Anything we deal with, we call it about like continuum mechanic. That means your system is large enough, there are enough number of atoms and molecules that they kind of fill the space continuously. Now give me another example. Or someone else. Should I go to the female part of the class? What is rigid?
I can't think of anything because I can't think of something that remains unchanged.
Good observation. How about diamond? Diamond is the hardest material, right? And they call diamond its girl's best friend. I think diamond is everybody's best friend because it's very expensive, right? Is diamond rigid?
Yeah.
So here's the thing. For diamond, we have Young's modulus too, right? You guys know what is Young's modulus, right? Or you don't know?
No.
Or you haven't taken C242? Okay, if you haven't taken, I'm going to cut it short. Remember, anything you have in whole universe, no matter how hard and strong it is, if you apply large forces, it's going to deform. If you make something out of diamond or titanium or whatever steel alloy, which is very, very hard and strong, if you make a large element of it, large part of it, and apply large forces, you're going to have some deformations, right? Nothing is rigid. When I say rigid, mathematical rigid, that means they remain perfectly same shape. So why and how we talk about rigid bodies here? Because imagine the body of your car. Even the wind flow can apply some forces, and those some forces can apply or create some deformations in the body of the car. Deformations could be in scale of micrometer or like sub-millimeter. But here's the question. If you drive your car, do you care in terms of analyzing the motion of the car? Or does it matter that one part of the car shrinks like 1 micron or 5 micrometer? Does it really matter? Really not. If you are dealing with a robot and the robot moves and the tip of robot deforms, because robots are like beams, right? When you apply, the beams bend, right? If the robotic arm bends by fraction of millimeter or by fraction of or few micrometer, does that affect its functionality? Really not, right? So in some very precise application, it could, and you have to consider, but in a lot of industrial application, if the tip of the robotic arm is like 5 micrometer off because of deformation, you even can measure it, right? So for this reason, we neglect those type of deformation, and most solids we deal with them unless it's something like a rubber things, right? Or kind of mushy, kind of doughy things. We consider them the rigid. So rigid body here is something like that. So a piece of wood, which you know is not rigid, if you hit it with hammer, it makes big dents. We consider rigid if you create like a mechanism for a toy or something. That is how the rigid body definition we use. Now, the type of planar motion, as I said, it could be pure translation. And I use the word pure, maybe is not the best word to use here. I'm used to use it because I'm immigrant. I probably use the words wrong way, right? But when I say pure translation, that means translation only. Okay? So it could be rectilinear, it could be curvilinear. You have rotation only, and you have general motion. These are three types of motion. I just explained it like 5 minutes ago. We're going to analyze, and we go one by one. Any question about the basic definitions we deal with here, rigid body and type of motions? Are we good? Haushin, you're good?
Yeah.
Okay. So translation. When we talk about translation only, any straight line in the body, in the rigid body, remains parallel to its original position during the motion. So that means it does not rotate. For example, if you have a rigid body like this and it moves on a straight line, you see, AB and AB prime remain parallel all the time, and point A goes on a straight line. Obviously, every part goes on a straight line. This is rectilinear translation. Very simple, right? A lot of reciprocal systems you have in mechanisms and machine have this rectilinear translation. Like this guy. Right? So it moves on a rail. It does not rotate. Every part of this kind of rocket-shaped car has the same speed and same direction, parallel moving together. It's not rotating. The other part of translation is curvilinear translation. Still, the line remains parallel, but it could move on a curved path. You see? Again. So AB remains parallel to its original shape or angle all the time, but moves on a curvilinear path. Example of this is swing like this. You may realize that this rectangular box moves on a curved path, but remains parallel all the time. So this is rectilinear motion, could be, sorry, this is a translational motion, could be rectilinear or curvilinear. Any question? Okay. Then we talk about rotation. The particles creating the rigid body move in parallel plane around the circles, which means if this is your rigid body, it goes like that. You have a fixed point, and the rest of the rigid body rotates about that fixed point. Example of that, like any type of pendulum, sometimes you have this, swings in the park that are not ropes or chain, they're like rigid rods. Those rigid rods rotate, around fixed point. It could be 2D like this, it could be 3D like that, that this rotates on the path. Another example, the blenders you use in kitchen to make shakes or whatever juice or things, right? The blade inside rotates about fixed point. That makes it rotation about fixed point. as I said, nobody uses mechanical watches anymore. Otherwise, you could have a lot of rotating elements inside that. Inside the car engine and transmission, there's a lot of rotational, components that rotate about fixed point. Then you have general motion, which is a combination of translation and rotation. For example, if this is your rigid body, it goes like that. It doesn't have to be curvilinear. It could move on a straight line kind of things. But the point is, the position of the particle changes completely, and the orientation of the lines also change. Example of that, this connecting rod in combustion engine. Look at this mechanism and tell me what kind of motion you see there. Heisey, what kind of motion you see here? We have obviously 3 moving elements, right? Link AB, link BC, and piston C. What kind of motion piston C has? Heisey.
I think it's translational motions.
Translational motion and is rectilinear, right? What kind of
Yes.
motion link AB has?
It's a rotational motion.
Rotation, because it rotates about fixed point A. How about BC?
I think it's also rotational motion.
I just wrote it here. Look at here.
Oh,
You're right. It has rotational motion and it has translational motion, right? When you say, remember, when we talk about rotation, is rotation about fixed point. This point A never moves, right? So AB goes around this. But link BC, it creates a very complicated motion going around. None of the points are fixed. You see, B was here, goes there. C was here, goes there. If you go all the way back, they could go the other side of the mechanism, right? So the link BC is an example of general motion. So technically, this mechanism gives you all 3 types of motion we deal with. Make sense? Now, another general motion, when you roll a ball, a disc, a circular shape on the ground, you see, that's how it goes. The tires of your bicycle or tires of your car have general motion because they rotate about their center, but the center moves, right? So you have a combination of rotation and translation. It gives you general motion. Here, you have another mechanism. This disc has rotation about fixed point. Link BC has rotation about fixed point, but link AB has general motion. This system, you have link ABC, which has general motion. Slider A, obviously translation, vertical, linear. Slider B, translation, horizontal, linear. So you have 2 translational motion and 1 general motion. So this gives you examples of what we mean when we talk about translation, rotation, or general motion. Any question? Now, when you ride your bike, give me another example of parallel motion, or sorry, translational motion. Hey, Ricardo, do you do bikes? Do you ride bikes? I can't hear you. I think you're muted.
It's really noisy outside, so I can't really hear you right now.
Okay, let me just
Yeah.
go to ask
That's-
someone else. Okay. Andrew, do you ride bikes?
Yes.
Okay. Give me example of translational motion. Some parts of the bike, when you move, when you ride your bike, has translational motion.
Would it be like the chain on the bike
The chain has a translation.
or like a piece of the um
Chain,
piece of the change just goes around?
well, from one wheel, from one sprocket to another, maybe it has translation, but around the sprocket rotates, right? Goes back and forth. So those tiny pieces rotate. Maybe that's not the best example. How about the body of the bicycle? Imagine you ride your bike on a road, kind of straight. The body of the bicycle does not rotate, just goes straight, like the seat, right?
Mhm.
What has general motion in addition to wheels, tires, when you talk, and also like a sprocket we talk? The pedals, right? When you use your pedals, they rotate technically about the center of the sprocket, but the whole bike is also moving, so it has general motion. These are examples of, when you analyze the motion of rigid body, understand what is parallel. The pedal itself, considering you put your foot in a certain angle, like horizontal, it goes up and down, is technically translational motion. If you do not tilt your foot, right, the pedal itself is always parallel to the ground and has a curvilinear motion, moves on a circle, but does not rotate. Does that make sense? So that's how we analyze the motion of rigid bodies. So I'm going to do this, ask you a question about this, and then we're going to stop it here. So you guys tell me what kind of motion we have here between the gear B and C. Two gears are engaged, rotating. What kind of motion we have?
Pure rotation.
Pure rotation, because each of them rotates about its center. How about this mechanism? Jake B, tell me what kind of motions you see here. We don't hear you. I think we still don't hear you. Okay, let me ask Yun. Yun, what kind of motions we see here? Are you talking? Because I don't hear you either. Do you guys hear him? Or is just me? No? Okay, Colin, how about you?
Would that be rotational?
Which one? We have three elements, A, B, B, C, C, D.
So DC and AB would be rotational and CB would be,
CB will be what?
I can't think of the word right now.
General motion.
General.
Okay. The last example, you have point B is fixed. You have a disk rotating here, a link connecting the center of the two disks. So B has rotation about fixed point. The arm AB also rotates about fixed point, but this disk D, the green disk, rotates and translates, kind of goes around that. So these two have rotational motion. This has general motion. These are examples of how you can categorize the motion of rigid bodies. And now you see, we talk about dimensions. We don't consider as a single point moving around because their rotational motion matters. Any question? I guess you guys have seen this robotic dog in the engineering building, right? This is a good example of, I think this has a nice music and the dog is dancing with music, but this has all general motions and most of them are 3D. Okay, so these are examples of different type of motion. As I mentioned in this chapter, we analyze them one by one from simplest to the hardest. Now, let me stop sharing and take a screenshot of class for attendance. Any question?
Yes, back in chapter 15, the very last problem.
Mhm.
I don't know how you got E equals 0.502, or I'm still working on trying to find E, so I couldn't like find D.
So there are two equations to honors. Anyone got the same numbers? Kelly usually calculate quickly. Did you get the same numbers or you have trouble too?
I was rushing too, but I did not get the same number for E, but I didn't check to see if my calculations were wrong or not.
Okay. Let's try to do it because I get the final numbers from the solution manual, but we can solve them here, no big deal. I'm going to continue solving this for a couple of minutes to finish the numbers. Anyone who wants to leave is 11:50. You are welcome to go and you are welcome to stay. Okay. So let's erase this for now. And I'm going to rewrite the equations, simplify them. So you have 0.8D for equation 1. And then you have 9.63 times 0.8 times 0.5. So this is going to be 3852. Then 12.84 times 6 times 0.5. Do we get the same equation? Let me do it one. The numbers look the same. 12.84 times 0.6 times 0.5. Okay, this is the first equation. The second equation, 0.6D plus 4.025. Here you're going to get 9.63 times 0.6 times 0.5 minus 2889.
What made you not have the 12.84E be negative? And why was the 0.6 times 9.63 negative?
Okay, good question. Here, look at here. This is the vertical component of velocity, right? Look at here. All right. When I project this, I get positive X and positive Y, right?
Yeah.
For tangential component, let's just go with blue. For tangential component here, when I get it, let's just go with this crazy dark. I get positive X, but you see this is negative Y. So when I put it here, for the Y, I put negative. Does that answer your question?
Yeah.
And then here we're going to get plus 5.136 E. Now, I'm going to calculate D from here. So D is going to be 3852 plus 3852 E divided by 0.8, which is going to be and then substitute in the second one. This goes to the other side, and this goes to this side. And then if you simplify this, we're going to get 4.815 times 0.6, 2.889 plus 2.889e minus 5. And I think this should be 5.1. Let me fix this. So this goes there, becomes negative. This 2 minus 5.136. You're going to get minus 2.247. E, yeah, this doesn't look right because E shouldn't be bigger than 1, and we're going to get E bigger than 1. Minus 6.914 minus 2.89. It's going to get minus 9.843. So your E becomes bigger than 1, which doesn't look right. We may have done some mistakes. I'm going to check that and post the solution later, okay?
Okay.
Because we may have made mistakes somewhere. Because E should be between 0 and 1. The E we get is like divided by 2.247. You technically get 4 something, which is not right. I'm going to double check where I have made a mistake. I can redo it next time or show you the, you know what? I'm going to complete this after here, after this part. And next time I show you the details, okay?
Okay.
Thank you very much. I will see you guys on Friday. You have your homework 3-4 already posted. And as I said, on Monday, we will have our midterm. So please do your homework, review this stuff. If you need help with any parts, let me know, okay? Thank you and have.
Will there be a test review on Friday, like what to expect?
No, we can't review because we may run out of time. If you get time, I may do review for final exam, but
Okay.
if you spend like 1-2 hours for review, here's the thing. You have seen the quizzes, right? You have seen the homework problems, and you have seen the problems we solve in the class. We're not going to go something off those. Some of the problems I solve in the class might be more complicated, like the one we did today, which takes longer time. Of course, this is for you guys to be exposed to the how to do stuff. You may not get something that complicated for the final exam because it takes forever to solve, to the midterm and final. Because remember, your midterm is going to be 75 minutes like a regular, and you probably get 3 to 4 problems at most, right? So you need to have problems that you can do it in 20-25 minutes. This is how, but if you're slower than the normal, right, you have to work on that. And I'm telling you, every single problem I have given to every single course, midterm or final, there are few students finishing quite early. So time, if you know what you do, time should be enough, right? But if you want to struggle and go back, specifically now, this looks like an open book, you know, exam, go to your notes and try to read and remember. You don't have time for that. But if you know what to do, start solving problem, you should be fine. The level of difficulty and what we cover is similar to what we have done. Like your quiz today wasn't complicated, right?
No.
Okay, so something like, there might be one problem with a challenge, but not everyone. Okay,
Okay.
thank you and see you guys on Friday. Goodbye.